calibration methods. So the whole idea of calibration methods is kind of like this guy going in the MRI machine, right? And I'm told these things are really loud. I didn't know that. I don't know why. Why don't they fix that? Why can't they? Why does it have to be so loud? Anyway, the point is that the guy is receiving a dose of radiation. You want to know what that dose is, regardless of the instrument or the technique or the method or whatever. You want to know exactly what the dose here is. So the only way to do that is to have things calibrated. Well, I thought this quote was kind of interesting. I think what caught my eye, other than the fact that babies shouldn't be over-radiated, was that this had been going on for some time. So, yeah, I mean, things got to be calibrated right. And what else does that MRI guy have to do? He just pushes the button. He should have that thing calibrated. Anyway, so there's different ways to calibrate, and we're talking about in the chemical laboratory. And there's some easy ways and there's some hard ways. It all really kind of depends on the sample, and how you're analyzing it. But we'll cover the general ideas how things go, and we'll start off with method of least squares. What happened to all the? Here they are. The method of least squares, Desiree, finds the best blank blank through data. The best what? The best what do you think I'm trying to say? All right, so you might have a bunch of data. Right. Now that may or may not be linear, but the method of least squares is going to find the best straight line through there. So if you're going to do this with a ruler, and hopefully the ruler's transparent, and you pretty much just try to weigh the differences, right? So you have just as much area above your line as you do below it if you're going to, try to draw a line through here, right? I don't know, it's something like this. So you'd have just as much area above and as you would below, right? That's kind of suspicious looking data though, because it kind of looks like it's kind of curvy. Anyway, best straight line. Now it only makes sense though if the data is theoretically supposed to be, Jackie, linear. Yeah, otherwise this whole idea isn't going to make sense. Okay. What is the equation for a straight line, Marlena? It was y equals mx plus b. Okay, so y equals mx plus b. Now that's when you plot what versus what here?
The x and the y.
Yeah, the y and the x, right? We'll plot the two. And we'll get a slope. Okay, change in y over change in x. If a least squares analysis is performed, so the least squares analysis is done, it gives you the best straight line through all your data. And like I said, it's not going to make sense if the data isn't linear in the first place. But it's kind of like, give you an example. If you have, do you remember using the little, I can't draw a cuvette. I just have to draw that for a cuvette. Remember cuvette, the word cuvette? You put cuvettes in what? Spectrometer, right? They call them spec 20 or these little boxes that gave you the absorbance numbers. So would you expect a linear relationship between those two, the absorbance and the concentration in the cuvette? Because the more concentration, the higher the absorbance, the less concentration, the lower the absorbance. That sounds pretty linear, right? So that you'd expect a linear relationship. So that'd be a good example of, oh yeah, let's plot absorbance versus concentration, okay? That's one where a linear fit should work. But I don't know if once you play this game a lot, you realize this is done kind of well because at really high concentrations, you kind of lose that linearity. That's why whenever if you're ever going to play with spec 20s or spectroscopy, just always keep things dilute and you'll be safe. But if a least squares analysis is performed on your data, what is the result? What's the result used for? What do you get, Jeff, when you do that least squares analysis? Find the data box in an Excel or whatever and highlight all your data and you get this regression analysis. What does it kick out that's so useful?
Trend
A trend line. Okay. Now, when he says trend line, what does that mean? Like, instead of my absorbance was my y equals m, x was my concentration, plus b. That was my x. The trend line, well, not enough English. It gave you little numbers. The regression analysis gave you little numbers for what? In this trend line, he called it, but it gave you little numbers for what? And this is the equation for our straight line. It gave us numbers for the slope and the y-intercept. Now, we wrote down the equation here. We just didn't identify this stuff. The slope is what symbol? M. There's my slope. The y-intercept is little b. So, I don't know if I could draw really well, I would. That's not so bad. Okay, so where did it cross the y-axis? All right, there's my b. And then you can calculate the slope, change in y over change in x. It does all that for you. Okay, it's kind of nice. But why is it so nice? What's so useful about this? So you know what this number is. Well, let's make it look better. You can have absorbance equals some number times your concentration plus some number. How is that useful? Exactly. Given one, you can find the other. You can go you plug in your little cuvette that, I don't know, Kimberly gives you. Hey, can you analyze my unknown for me? I don't want to go through and make all this calibration curve, but Monica, yours is so nice and linear. Just run my unknown on yours. So Monica takes Kimberly's solution, dumps it in her little cuvette, puts it in the machine, gets a number for the absorbance. Well, all she has to do now is solve for concentration. She'll know what the concentration is in that cuvette. It's really powerful. As long as it's the L word, linear. Otherwise, forget it. It ain't going to work. Okay. So now there are some assumptions for this magical least squares analysis to work. Okay? And here's two of them. Delta y is much, much bigger than delta x. What the heck are they talking about there? Delta. What's delta? Change. So something's fluctuating, right? You put in it, I don't know if you really noticed it, but if you spend more money and get a much larger instrument, like the one up in 415, research grade spectrophotometer, instead of getting a little absorbance measurement that's 0.2, it says the absorbance measurement is 0.2021, 0.022, 0.023, 0.019. See how it's bouncing around? Because it's an active measurement. It's not, there's error there. So it's bouncing around, right? So they're hoping, in order for this to work really well, the error in the y, the error in the absorbance, needs to be much bigger than the error in the wavelength. So in other words, have a monochrometer, well, you guys don't know what a monochrometer is, have the instrument characterize the wavelength in that spec 20 really, really well. And the absorbance measurement can bounce around a little bit. Just don't have it the other way around. Okay. All the error and the y are approximately the same. What that's kind of getting at is that if I have really high absorbance, right, they're trying to say that the error in the y doesn't matter. You can have really put it in something that makes sense. Really small absorbance measurements, really high absorbance measurements. It's still bouncing around at whatever measurement, whatever resolution, 0.01. It's still always bouncing around the same spot. Okay? But that's not true. In real life, it's not true. So that's what I was saying. If you ever do use a spec 20 or spectroscopy, just keep everything dilute, because this is a real problem. The errors aren't the same, especially at really high absorbance values. But that's information you don't even need to know. But you lose your ability to do least squares analysis. So all the error and the y are approximately the same. And that's true if you keep everything dilute with a spec 20. So, but that's, to me, this is the real power, right? Just make that, just do a really good job and make your calibration curve really nice. Get it nice and linear, and then you're set. Okay. So let's play around with this linearity idea a little bit. That's what this is here for. Assume separate experiments are performed where each experiment matches one of the below theoretical equations. Okay. Pick two variables that are linearly related to allow a least squares analysis to be performed. So what I'm talking about here is, like in this equation, pick two variables where you would get a linear relationship between them mathematically. And we already know the answers y and x. Okay. What if you plotted this one? You could plot, well, here this is y versus x. In this one it would be, you could plot VF versus t. Now if you did VF versus t, what will your little slope be? Your little slope would be a, all right? And your y-intercept would be? Everybody be v? Yeah, v initial. Okay. What if you plotted something else, though, in that same problem? What if you plotted VF versus VO? Some Joe just wanted to plot that. What would they, and according to this equation, I don't know if you remember this equation from general physics, but this was just to remind you, right? You've got final speed, initial speed, acceleration, and time, but that's neither here nor there. The point is it's the math is what I'm after. So I'm plotting VF versus VO. What would be the slope? What would be the y-intercept? Right? So what you do is you let this equation tell you. The slope would be 1. I think she's played this game before, maybe, or maybe not. Right? Whatever you're plotting, this can be whatever you want. Right? That's on the x-axis. And on my x-axis, it's v0. In front of that v0 is a 1. Right? So, because whatever's in front of the x is my slope, so this would be 1. What would be my y-intercept? It has to be plus whatever's left over, so it would be at. What could I plot in this one to get a linear relationship? I want to get a linear relationship. Jeff, you have a guess?
D versus G.
I could plot D versus G. If I plot D versus G, my slope would be, my y-intercept would be. Does anybody see it? He said D versus G. So what's in front of my x is my g. What's in front of my g then? 1/2 times t squared. That would be my slope. Well, my y-intercept would be 0. So I don't know if you recognize this equation. D is 1/2 gt squared. But you drop something after a certain time, and d is how far it fell. Well, is my slope changing with time? M is 1/2 t squared. So it's changing with time big time. So I'm not going to have a linear plot here at all, because look at my slope. It's 1/2 t squared. So that wouldn't be a linear relationship. I wouldn't plot D versus G. What could you plot? And you will get a straight line. D versus, let's try D versus T. My slope is what? My y-intercept is what? My slope is going to be, now pull out a, let's see, here's my equation. Pull out a T, what's left? 1/2 t times g, because it's all there. I've still got my t in there. My slope is still going to be changing with time. So that one won't work either. Let's try that one. Let's plot d versus 1/2 g. My slope and my y-intercept. If I pull out 1/2 g, what's left? T squared. Still, all right, my slope is still changing with time. At least that guy's still 0. So that won't work either. I think there's only one possibility left. T squared. Plot d versus t squared. So my slope, everybody would be what then? 1/2 g. And my y-intercept, everybody would be 0 plus. It's plus whatever's there. Okay, so this is it right there. And this is the power of understanding this stuff. Because you could take, if you understand the physics, I guess, d is 1/2 gt squared, take an object and drop it, measure a bunch of the times, measure the distances they fell. You just got to square the time, right? And the slope will be 1/2 g. Make the plot of d versus t squared, calculate do the regression equation, get the slope, because theoretically it's supposed to be linear. Set that slope equal to 1/2 g, and you can actually get the value of gravity. Okay, so it's powerful stuff if you just play around with it a lot. Okay. Oh, let's just finish the story. Okay. I want a linear relationship. A linear plot. I want a linear plot between, I don't know, two things. What could I say? I don't know, you don't know what anything is, though. I guess what I'm saying is I could plot f versus, let's just see if you're seeing this. If I plot it versus m squared, f versus m squared. I just forget this I want stuff because you'd have no, it doesn't make any sense. F versus m squared, big M squared. There's my y. Here's my x. What would be my slope? 6. I think you see the game now, right? Slope would be 6. Okay, that's enough. Calibration curves. So why would it be easier, do you think? All right, so we need to make a calibration curve first. Let's say we want absorbance and concentration, just like we were talking about before. And we need to make a little table, absorbance versus concentration, and make some concentrations of solutions, right? Maybe 3 standards or something. And then we'll measure their absorbances. Put them in the little Spec 20 machine and get their absorbances. So I've got 3 points. So I guess I should just have 3 data points. And then we plot them. And we have a calibration curve. And then we can do the whole game we played before of, you know, getting something like this, getting the regression, and we can actually calculate concentrations of unknowns just by measuring the absorbance of the unknown. Okay, why is a linear calibration curve preferred? Why would it easier? It's kind of a silly question, but I just want to start somewhere. Brandy, what would you think? Why is a linear calibration curve easier than?
It's easier to get the slope.
Yeah, otherwise you can't get a slope, right? So if it's linear, heck, if it's linear, all you really needed were those 2 data points. If it's linear, you don't even need a lot of data points. Okay, it's a lot easier to make a calibration curve. And if it's not, also if it's linear, you can do that whole linear regression thing. Okay, now some terminology. How is an external standard calibration curve prepared? And how is it used to determine concentrations of unknowns? So it's just terminology. I think you already know the answer. External standard calibration curve. That's this. right? Make up a bunch of standards, right? Here's 3 of them, and here's some stock solution, right? We can do that whole MIVI equals MIVF equals MFVF game and calculate the concentration of our standards from this stock solution, just by taking out, right, different little amounts of VI and putting them in, filling them up to the mark. There my VF would be 250, right? So we could make some standards from a stock solution, and then we put it in the machine. So that's all external standard is. It's just a fancy word for making standards, right? Okay. And how is it used to determine concentrations of unknowns? Well, we already talked about that, right? Right? Do a regression analysis, and you can finish the sentence. Make a trend line, like what Jeff was saying, or just more simply, just say do a regression analysis and get the values for the slope and y-intercept. So then you can calculate the concentration of anything that you put in there. All you have to do is measure its absorbance, right? Because then you would have, right, some number equals some number times the, oh, sorry, that's just, you'd have absorbance plus a number. Remember that game? So you know what the slope and the y-intercept are. Okay. What if the response signal of an unknown is above or below that of the standards? What then? Ooh, that's a good question. See what I mean? So we made standards from, I don't know, this number to this number. What if your unknown has absorbance way the heck up here? Let's make it red. We're way up here. Your unknowns. You want to go across, right? Don't you want to go across and come down? That's what you'd like to do. But can you? Or are you supposed to? Does it seem like it would be good practice? Your life depends on it. Some dude in court for his cocaine in his blood's dependent on it. You have to make standards that are above and below what you're analyzing, because there's no guarantee that it's linear outside that range. So if the response or the signal of your unknown is above or below that of the standards, make more standards, right? You have to. You have to make more standards. So you have to make, make it so that the standards cover everything you want to analyze, above and below, in signal, and therefore concentration. If the unknown is in a solution of Elmendorf lake water, will the calibration curve still work? So first, you picture my calibration curve here, right? This is, I don't know, which blue is some really carcinogenic material that's just horrible, right? Just pretend, right? Just horrible, horrible stuff. And here's an unknown that you pulled from the shelf, and oh geez, I mean, I read online that you can dump this stuff down the drain if it's below a certain concentration. So can I dump it? Or will it kill the rat because someone just fed it to some rat, right? So make a calibration curve. I'll pull out known volumes of this, right? Fill it up to the mark. MIV equals MFVF. Calculate the concentration in all these guys. Plot it out. Run this unknown, right? So this all looks hunky-dory. External standard calibration curve. What if this poison was in Elmendorf lake water? Now, right? There's some blue stuff in here. Do you see a problem? Right? I want to put this stuff in the cuvette, right? And use that same calibration curve? Does that sound like a good idea? Right? Does that sound like a good idea? Because look how this is absorbing all these different wavelengths. there may be no poison at all in here. And you put this in a little cuvette and see what it does, it's going to tell you that there's a signal there. I mean, it's horrible. It's a mess. Right? So there has to, but this is real life. This is real life. This is fantasy land, right? In real life, you're never going to have this nice, beautiful unknown that's so clean and clear. This is, man, I want to know how much, I don't know, iron's in my water. Well, this is what they give you. Right? Whatever you're trying to analyze. There's an oil spill. How much oil was on the beach? This is what they give you. They go out to the beach and they scoop it up. So, standard addition technique, really powerful. Okay, that's what you need to do. Now, it's just another piece of terminology. What is meant by the matrix of the sample? Sample matrix. If we jump back and we talk about external standard calibration curves, we were just talking about these guys and making up standards. The chemical environment of the blue dye, now the word for what you're always looking for starts with an A. The analyte. So analyte is what I'm always looking for. That's their word. So the chemical environment of the analyte is the same everywhere in here, right? It's the same in my unknown as it is in my standards, because everything's made up with water. It's the exact same chemical environment. They don't like to use the word chemical environment. We're going to use the word, starts with an M, matrix. Exact same matrix. So if we're going to do the analysis, we need to have the exact same matrix. But this is our matrix. It's Elmendorf water. Well, that means you got to use Elmendorf water to make the analysis. Okay? And that's what standard addition technique does. It matches the matrix between your standards and your unknown. So you have to use the unknown to make the samples. How do they do it? Okay. So first, they do have a stock solution, because you have to have a stock solution of what you're interested in. So let's just do one piece at a time here. This is no longer our unknown. No. This is our unknown. So analyze that for poison blue. You still need a stock solution of this poison. Okay, we got it. That's what this guy is. Our unknown solution. Great, that's our Elmendorf. Okay, so here they have 4 identical flasks. Great. 4 identical flasks, all there. And what they want you to do is, see in their colors here, put the exact same volume of unknown solution in each one. They don't even care. Just put the exact same volume in there. So, I guess you have to get some kind of pipette or graduated cylinder or something, and just dump the exact same volume of Elmendorf water in each one of those flasks. Done. Okay. Now, see what the orange? They dumped in different volumes of the stock solution. So notice in the first one, they didn't dump any though. So we won't put any in this one. And in this one, maybe we'll put 1 mil. Better label it 1 mil though, you'll see why. And this one we'll put 2 mils of our stock solution of this. And this one maybe 3 mils of our stock solution. Okay, great. And then we need to fill them all up to the mark with water, right? So, and that's what you do. So they all have the exact same final volume. Okay. And then whoa, what happened here? Oh, because I hit enter. Where's my equation? I'm going to have to copy your guys's. I lost it. What is the concentration of the unknown? We make a plot. Is yours even there, or does it just disappear? Make a plot of the volume of the stock versus your signal. Okay? Make a plot of the volume of your stock versus your signal. Yeah, yours showed up. What happened to mine? Okay. This is the one I did in part. Thanks, Jackie, because I don't remember this part. The concentration of the unknown, let's just copy this equation you got. B, C, standard, M, V, UNC. Okay. So you recognize little m and little b? Andy, you recognize little m and little b?
Slope and minus
Slope and y-intercept. That means you're going to have to do a what analysis, Danielle? Search Lennar. Or you're going to have to do a regression analysis on your data. Okay? VS stands for volume of stock, right? Because remember, one I added 0. Another one I added at, what did I say, 1, 2, and 3 mils or something. So one of them has 0. Okay. But it still gives me a signal. And then the rest. So the volume of the stock that you put in each flask, oh, I think we had 4 flasks, so we'll still have 4 dots. So plot the signal that you get from each of these solutions. You have to put them all into the spectrophotometer. Okay. Fill up the cuvette. Do a regression analysis on it. We get the slope and the y-intercept, like you said. V is the volume of stock. How about CSTD? Concentration of the standard. Read it off the bottle, right? Concentration of the standard. How about VUnc? Volume of the unknown. I forget what I said. I thought however much unknown we dumped in each one of these flasks at the very beginning of Elmendorf. So whatever that is, you put in right there. So multiply your y-intercept times the concentration of your standard, divided by the slope, divided by the volume of unknown that you put in each one of those standard edition flasks, and you get CUnc. Kimberly, which is concentration of the unknown. The concentration of that blue dye in this ugly mess. Why does it work? Because we match the M word, Gloriana. We match the matrix. In all of our standards that we made, we match the matrix. It has to work. It does work. It's a really powerful technique. Standard addition technique. Internal standard. Okay. Gases are difficult to sample reproducibly because sampling fluctuations are a common occurrence. A sampling fluctuation, what did the sampling... Now we picked on Danielle. Who haven't I picked on? Marlene, I haven't picked on you. What's a sampling fluctuation? What do you think that would be?
Fluctuation in sampling.
Yeah, fluctuation in sampling. Let's say you're grabbing pebbles. So with your hand, you're grabbing pebbles. A sampling fluctuation would be one time grabbing maybe 110. The next time you're grabbing 5. Hopefully you're grabbing a little more than that, right? So the fluctuation shouldn't hopefully isn't that big, but 110, 100, 115, right? You're just grabbing different amounts because it's really hard to grab the same number of pebbles every time, especially if they're tiny. A gas is even worse. So what they do is they use what's called an internal standard. Now we've had an external standard. That's everything we've been talking about so far, right? We use an external standard to make known concentrations, and we call them external standards. And we made external standard calibration curves. That's everything we've been talking about so far. And do you remember what we did is we plotted the signal versus the concentration of that external standard. Right? That's what we've been doing this whole time. And then we get our little plot. Right? Everybody with me so far? That's what we've been doing. That's what we've been talking about. Okay? And now what they're saying is, okay, this is your gas. You're going to sample this gas 2 times. And let's say you're after the X's or the stars. And this is sampling, I don't know, sampling A. Here you sampled it B. So let's put a bunch of more of these guys in here. So this time you got a little bit more. Okay. So if you're sampling a gas, now, but you just did the same thing twice, but now you have more signal. There's a problem. Yeah, you're not going to be using cuvettes in a Spec 20 anymore. Now you're sampling a gas. What's the fancy technique you've heard that samples a gas? Really powerful. They call it GC or gas chromatography. Really powerful. but you're sampling a gas. So sometimes you don't sample enough, sometimes you sample too much. Your signal's bouncing all over the place. So what they're going to do is not just, here's our external standard, right? We made up our samples, there's our external standard. What we need to do is we need to also introduce a second standard. And this one that behaves the same, let's maybe make them, I don't know, red or something. Call them O's, okay? So in your standards, how do you draw a flat? I'll just draw a box. How do you draw a beaker? Draw a beaker. That looks like a beaker, right? So in my solution, I have my internal standards, and I have my analyte or my external standard. So you have, this is what you're analyzing. You have to make up that solution, right, and make up a bunch of them. So, and you sample it, put it in the instrument, you get this signal. So you sampled a lot of the analyte, a lot of the second one, they call it the internal standard. But now if you sampled more, well, that means you're going to get even more of the stars. We're going to get more of the O's too, right? If you sampled more. Wrong color. Does this make sense? So if I sampled too much, well, then I sampled too much of the O's too. So the only thing that changes, how does this introduction of this internal standard, these O's, how does this solve the problem? What do you have to do to the plot? Don't plot just the signal of this guy. Plot the signal of that divided by the signal of the O's. If you do that, notice how the signal for the stars in A here, there's like 4 to 2. If you sample too much, so the ratio is about twice 2 to 1. Here in B, hopefully the ratio is still around 2 to 1. You just sampled too much. So you sampled too much of your analyte, and you sampled too much of your internal standard. So it just keeps the ratio the same. That's how it cancels out sampling fluctuations, by introducing an internal standard. So you just have to make sure this guy is really well mixed, and that the internal standard behaves the same as your external standard that you still have in there. So that's what happens with analyzing the GC. If you have to, you should introduce an internal standard. And it seems like twice the work, because now you have to measure 2 signals, not just 1. Okay, there it is, internal standards and gas chromatographic analyses. Okay. Here's our first problem. Suppose that you carry out an analytical procedure to generate a calibration curve like that shown in figure 4-11. Then you analyze an unknown and an absorbance that gives a negative concentration for the analyte. Huh. So you get a negative answer. How can you get negative concentration, right? You go, everything looks so pretty, right? You calculate your y equals mx plus b, or in this case, you know, absorbance equals my slope number times my concentration plus my little y-intercept. So, right, these are numbers. You go through the work and you calculate what your concentration is, and you get a negative answer. What does that mean? Oh man, I think someone only, you have to have instrumental analysis for this to make sense. How is it possible to get negative absorbance? Man, I think this is too technical for you. I should get rid of this question. But since we're there, I'm going to answer it. You put a little cuvette in a spec 20, right? You're supposed to get positive numbers, right? If it's not absorbing at all, you should get what number? 0. So how can you get a negative number? It happens, especially if Desiree just put all this stuff on her face and she's got all this lotion and she gets it all on the cuvette and just, right? So now a lot of light is being absorbed. what happens is that absorbance is really two measurements. That's why I'm saying this is too technical. But I don't. Whenever you measure absorbance, you're measuring with respect to a background. So I don't know if you remember pushing the little 0 button, right? When you're doing a little spec 20, you had to put your cuvette in there with maybe just water, and you push the 0 button. I don't know if you remember doing that, but you should have. If you didn't, you should have. So you want to measure the absorbance at 510 nanometers. So you put your little cuvette with water in there, you push the 0 button, and then you put in your sample to get the absorbance. Well, my story was Desiree had all this lotion and stuff, and then she gets it on the cuvette and she puts it in there, and that's when she pushes 0. Well, now this background is actually going to have more absorbance than what your sample will, because then you put in this nice clean cuvette for the sample. So when the background absorbs more than your signal, that's how you get a negative absorbance. That's a bad question. Doesn't belong there. Okay, this one does. This is a good one. Using the calibration curve in figure 4-11, find the quantity of an unknown protein that gives a measured absorbance of 0.264. Blank has 0.095. Okay. So we need the equation for a straight line here. Can you make it out? I don't know, let's just pick one. So y equals 0.0163, right? X, and I'm just leaving those uncertainties out because we don't need them. 0.005. Okay, so here's my equation for my straight line. And what they're saying is right, instead of saying y, we could say absorbance, because I'm trying to fit this, match this. I could say absorbance. And instead of x, I could say, in that plot, it'd be what? Instead of x, I could say amount of protein in, oh, can you recognize that unit? Amount of protein in micrograms. It kind of looks better than just writing y and x, I think. Okay. So they're saying that you made a whole bunch of standards with these proteins, right? You did a regression analysis on it after measuring absorbance of all these standards that you made, all these external standards, and you came up with this regression equation. Okay. You measure an unknown, and you get 0.264. A blank has an absorbance of 0.095. Why are they telling you this? What do they want you to do? So in your unknown of 0.264 absorbance, is all of it due to the protein? For some reason, they didn't push the 0 button. They actually measured what the absorbance was, 0.095. They want you to subtract 0.264 minus 0.095, and that's the signal of your unknown. So that's the number that goes in for the absorbance. They want, that's what, I don't know if you recognize that, but that's what they want you to do. And we're almost out of time here. Take the 0.264 minus the 0.095, and then you just solve for your amount of protein in micrograms. Okay? Make sense? Kelly, that makes sense? All right. So I copied the equation just from the table up there. Okay? So there's always more questions than we can cover, but that's okay. So have a good day.